Hello everyone. Today we are going to discuss about motion in a plane. The arc of a ball, the orbit of a planet, the turn of a car. One simple tool describes them all. The arc of a ball, the orbit of a planet, the turn of a car. One simple tool describes them all. See here that one simple tool that describes everything. Beyond the straight line, mastering motion in a plane. This is, you see here, this is one dimension motion. This is 0, this is positive, this is negative. In a two-dimensional motion, this is x direction, this is y direction, and this is the particle is moving in this direction. In one dimension, motion is simple. An object can only move in two directions, which we can label with plus and minus sign. The challenge. But how do we describe the rich, complex motion we see everywhere in our two-dimensional world? A simple plus or minus sign is no longer enough. We need a new language to explain the two-dimensional motion. Now you see what you get. The next one is the two languages of physical quantities. First one is scalar quantity and the another one is a vector quantity. A quantity with magnitude only. It is specified by a single number and a unit. What are the characteristics? Combines using the rules of ordinary algebra. Suppose distance 3 meter, it is a scalar quantity. Mass is 2.7 kg. 2.7 kg, it is a scalar quantity. Temperature 35.6 degrees centigrade, it is a scalar quantity. Vectors, a quantity with both magnitude and direction. It must also obey the triangle or parallelogram law of addition. We have two laws, three laws we have: triangle law of vector addition, parallelogram law of vector addition, and polygon law of vector addition. Now see the characteristics requires a special algebra to combine. These are the different vector quantities. The displacement, it has direction and magnitude both. Velocity, it has direction and magnitude both. Acceleration, it has velocity, it has direction and magnitude both. And force also. Force also, it has magnitude and for both. So this is the difference between scalar quantities and vector quantities we need in two dimensions. That's why the two language of physical quantities. Now we learn this one, that next thing, that is, so we define scalars and vector quantities here. Now we learn another thing that is this one: pinpointing, positions, and charting displacement. Here you see this is the actual path, this is del r, this is position vector p, this is final position vector r. Therefore this is the distance del r, this is that, or this is the, suppose this is the actual path. So the displacement vector will be del r, r dash minus r. This is the displacement vector. The displacement vector del r is the shortest straight line between the initial and final points. You see, this is the initial point and this is the final point. So what we are getting, you see here, the displacement vector del r is the shortest straight line between the initial and final points. It does not depend on the actual path undertaken. The magnitude of displacement is therefore less than or equal to the path length. Therefore, you can say the magnitude of the displacement is therefore less than or equal to the path length. This is displacement vector and it is the shortest distance. And we find in displacement vector, we only need the initial point and final point. No need of actual path. So, we have to remember that these two things, that is scalars and vectors, are very much important for defining these things. And the next thing you can see here is, you see this is the actual path, and so data can be written as r dash minus r according to vector law of addition. Now we'll do another thing, that is this one. The Faces toolkit, manipulating vectors, multiplication by a real number. You see here this is a vector. If we double the magnitude, remaining the direction same, it will be 2a. If we change the direction and we multiply it by 1.5, it will be minus 1.5 a vector. Multiplying a vector a by number lambda creates a new vector. If lambda is positive, lambda equal to 2, the new vector 2a has the same direction but twice the magnitude. If lambda is negative, lambda equal to minus 1.5, the new vector minus 1.5a has opposite direction and 1.5 times the magnitude. The null vector, and what we call it as zero vector. You see here, this is a vector with zero magnitude and an unspecified direction. No direction, unspecified. This is known as zero vector. Creating here so a vector with zero magnitude and an unspecified direction creation results from a plus a minus equal to 0 or 0 into a is equal to 0. Physical meaning: a null displacement vector means an object has returned to its starting point. That is zero vector. Plus vector minus a vector, that gives a zero vector, and it has unspecified direction. A vector with zero magnitude and an unspecified direction, that is known as null vector or zero vector. Now we go to the next one, that is this one. Combining vectors, two methods, one result. Here see, head to tail triangle method and method 2 parallelogram method. In this method there is n vector, there is another b vector, and if we add this one, place the tail of a vector b at the head of vector a. Resultant r equal to a plus b is the vector drawn from the tail of vector a to the head of b. This is the resultant vector a plus b. Method 2 parallelogram vectors. This is vector a, this is vector b, right? And place the tails of vector a and vector b at a common origin. Complete the parallelogram. The resultant r is the diagonal starting from the common origin. That we are getting the resultant, and that is vector a plus vector b. Now vector addition is commutative. That is a plus b is equal to b plus a. You see here a plus b is the resultant, or b plus a having the same resultant, having the same magnitude and same direction also. We will find these things. You see here the power of components from geometry to algebra. Any vector a in a plane can be broken down into two perpendicular component vectors, one along the x-axis and one along the y-axis. You see here, this is the origin, this is ax, this is ay, this is I unit vector along x direction and j unit vector along y direction. This is vector a, this is angle theta. So vector a can be represented as axi plus ayj. Finding components, you can find the component ax equal to a cos theta and ay is equal to a sin theta. Rebuilding the vector, modulus of a can be found out of root over x square plus a y square and theta equal to tan inverse of ay by x. By resolving vectors into components, we can see simple algebra on each axis separately. Now we go to the next thing, that is this one. Vector addition made simple. The analytical method. The problem. Graphical. Addition is visual but can be tedious and inaccurate. Solution: add the corresponding components of the vector. Right? Suppose there are three vectors: a vector, b vector, and this by vector. A vector can be represented as axi plus ayj, and b vector can be represented as bxi plus byj. So we find here that this is Rx equal to x plus bx. This is why we can change into the corresponding components, right? Here you see these can be Rx can be represented x plus bx. Rx means in this direction, Ox direction. Rx equal to we are getting ax plus bx, same direction, and by this one ry equal to ay plus by. Okay, therefore r equal to x plus bxi plus ay plus byj. So this is the resultant vectors, right? This made simple by combining or changing into the components of the vectors along x direction and along y direction, right? Now we'll find this is the addition of vectors. We'll find the next thing, that is the great insight: two motions for the price of one. Motion in a plane can be treated as two separate simultaneous one-dimensional motion. You see here, this is the Vx, Vx, Ax equal to 0, and this is the Vy, Ay equal to minus g. X direction constant velocity, y direction constant acceleration. Here the constant velocity is there in x direction, and in y direction constant acceleration. The horizontal motion, x direction, and the vertical motion, y direction, are independent of each other. They occur at the same time but do not affect one another. Our vector toolkit allows us to analyze them separately and then combine the results. It was Galileo who first stated this independency of the horizontal and vertical component of projectile motion. Application 1. The physics of a projectile. What is that? A projectile is any object that is thrown or projected and then moves under the sole influence of gravity, neglecting air resistance. The setup: an object is launched with an initial velocity v0 at angle theta 0 to the horizontal. The physics applying superposition: horizontal x direction, no acceleration x equal to 0. The horizontal velocity Vx is constant. Vertical y direction, constant downward acceleration due to gravity, Ay equal to minus g. Therefore, initial velocity component v0x equal to v0 cos theta 0 and v0y equal to v0 sin theta 0. Deconstructing the parabola, the equations of motion. Here this is Vx, this is Vy. Position at time t, xt, v0 cos 0 t theta into t, y equal to v0 sin theta t minus half gt square, and velocity at time t equal to Vx equal to v0 cos theta 0 and Vy equal to v0 sin theta 0 minus gt. These four equations you have to remember. Now equation of a parabola, equation of a path is a parabola. By limiting t, we get the shape of the path y equal to tan theta 0 x minus g by 2 v0 cos theta 0 square x square. And you know that the equation of a parabola is y equal to x plus b square. You say y x, a is tan theta 0 and b is g by minus g by 2 v0 cos theta 0 whole square, that is b. So this is the equation of a parabola. We are getting the as equation of a parabola. Now the next thing is this one, key metrics of a projectile's flight. You see, this is the maximum height, this is the horizontal range, and this is the time of flight. These three things we need Maximum height HM, the peak of the trajectory HM equal to V0 square sin square theta 0 by 2g. Time of flight, the total time of the projectile is in the air. The STF total time of flight is 2v0 sin theta 0 by g. And horizontal range, the total horizontal distance covered are equal to v0 square sin 2 theta 0 by g. Insight, the range R is maximized when sin 2 theta 0 is maximum, which occurs at the launch angle of theta 0 45 degree. If this angle is 45 degree, then the range will be maximum. So the athletes throw ball or javelin at an angle of 45 degree to reach the maximum range. Now we learn the other things, the application 2, uniform circular motion. The motion of an object traveling at constant speed along a circular path. The core paradox. The object speed, a scalar, is constant. However, the direction is continuously changing. Since velocity a vector includes direction, the velocity is not constant. A change in velocity means there must be an acceleration. A change in velocity means there must be an acceleration. This is uniform circular motion. The motion of an object traveling at a constant speed along a circular path. Object's speed is scalar is constant. However, its direction is continuously changing. Since velocity inputs direction, the velocity is not constant. A change in velocity means there must be an acceleration. And whenever there is acceleration, there is a force. The center seeking force. The center seeking force. Now we find the center seeking force. The center seeking force, centripetal acceleration. You see here direction. The acceleration in uniform circular motion is always directed towards the center of the circle. This is called the centripetal acceleration. Magnitude. The magnitude of the centripetal acceleration is constant and depends on the object's speed and the circle's radius. In key formula, in terms of linear speed, linear centripetal acceleration equal to v square by r. In terms of angular speed, omega equal to omega square r. Note, since the direction is always changing, centripetal acceleration is not a constant vector, even though its magnitude may be constant. Centripetal acceleration is not a constant vector, even though its magnitude may be constant. You see, this is large T, this is small t, and this is limit del t tends to 0 at this point. At that time it is perpendicular to the radius. B is perpendicular to the radius. So this is the center seeking force or centripetal acceleration. The acceleration in uniform circular motion is always directed towards the center of the circle. This is called the centripetal acceleration. The magnitude of centripetal acceleration is constant and depends on the object's speed and the circle's radius. So the key formulas in terms of linear speed x equal to v square by r, in terms of angular speed s equal to omega square r, and note, since the direction is always changing, centripetal acceleration is not a constant vector, even though its magnitude may be constant. A new framework for seeing the world. Journey recapped. We faced the challenge of describing motion beyond a straight line. We learned the language of vectors. We account for both magnitude and direction. We mastered the toolkit of vector operations, especially the power of components. The ultimate payoff. The principle of superposition allowed us to deconstruct complex 2D motion into simple, independent 1D motion. With this single framework, we can now precisely analyze the parabolic arc of a projectile and the constant acceleration of an object in a perfect circle. So, this is what we have learned. All these things is a new framework for seeing the world. This journey recapped and the ultimate payoff. Dear friends, if you like this video, please subscribe, like and share. And thank you everybody for watching this video.